would like to really thank the organizers, in particular Koji, we just mentioned, for inviting me. This is the first time to attend the AAL conference one this year. I'm going to share some research of mine on preference logic. I'm going to, I have 70 minutes. My plan is to finish in 60 minutes, leaving about 10 minutes for discussions. Preference, let me start with the work by Fenrong in 1963. He published this book called The Logic of Preference. In his book, he started with the discussion on the notion of preference. Namely, he wanted to answer the question where preference stands. Then he distinguished three categories of the philosophical notions. The first one called deontological, we usually call normative notions, like notions of a right and duty, command, permission, and prohibition. The second one is called axiological, like the notions of good and evil, the comparative notion of betterness. Then finally, anthropological, the notions like need, want, decision, choice, motive, end, and action. Then he said that the concept of preference stands between the two groups of concepts. It's related to the axiological notion of betterness on one side, but it's related just as well to the anthropological notion of choice. This has been apparent if we look at the literature. Actually, if we think of the deontic logic, in fact, preference semantics has been dominant too. So basically, one could say the notion of preference is really occurred in these three categories. Then I want to mention two issues in Fenrong's work. The first one is a distinction between intrinsic and extrinsic preferences. This is a quote from his book. He said, a person says, for example, that he prefers claret to hock because his doctor had told him, or he has found from experience, that the first wine is better for his stomach or health in general. In this case, a judgment of betterness serves as a ground or reason for preference. I shall call preferences which hold this relationship to betterness extrinsic. This is the extrinsic preference. It could, however, also be the case that a person prefers claret to hock, not because he thinks the first wine is better for him, but simply because he likes the first better. Then his liking the wine better is not a reason for his preference. So this is a clear distinction between extrinsic and intrinsic preferences. Put it slightly formal, the difference is principally that P is preferred extrinsically to Q if it is preferred because it is better in some explicit respect. If there's no such a reason, the preference is intrinsic. So this is the first one. The second issue, in fact, is about the dynamics of preference. So we know by our experience, we often change preferences because of various reasons. I'll show a few examples later. But in Fenrong's work, after his discussion about a notional preference, he wanted to set up what he's going to study in his book. Then he ends with this quote. He said, "The preferences which we shall study are a subject intrinsic preferences on one occasion only." That's a topic he was focusing on in his book. Thus, we exclude both reasons for preferences and the possibility of changes in preferences. So reasons for preferences, that's the notion of extrinsic preference, and possibility of changes, that's the dynamic preferences. So in fact, these two aspects has been taken up to some extent after his work. For instance, like in the Handbook of Philosophical Logic, Hansen has a chapter on preference logic, and the decision theory and game theory are using the notion of intrinsic, so they develop further. For instance, utility function is usually being used as a representation of preference, and then preference change, given that dynamic logic was proposed in 1970s, 80s. So in Bentham 1993 made a first attempt using dynamic logic for characterizing the dynamics of preference. And we also know AGM style of belief revision. Inspired by this, Hansen, Sven Owen Hansen, 1995, also proposed some postulates, which is similar to belief revision postulates, studied 4 basic operations in preference change. So those are the major research after Fenrich's early work, 1963. I also want to mention Howden 1957. That's the logic of betterness. It's also very important in the history of the preference study. So in my work, I basically, as I mentioned now, these 2 aspects, reasons for preference and dynamics of preference, are my main research topic. And today, I'm going to share some results from this book, which published in 2011. So I'll focus more on conceptual issues, ideas, and I will not say much about concrete like proofs for some theorems, but I'll say also some ideas of certain important theorems. If you are interested in, you can look at further details of the proofs in the book. I'll show a few examples, because these 2, my example will be running examples I'll use for today's tutorial. The first example, Alice is going to buy a house. She considers 3 things: cost, quality, and neighborhood, strictly in that order. All these are clear-cut. For instance, the cost is good if inside her budget, bad otherwise. Her decision is then determined by the information whether the alternatives have the desirable properties, and also by the given order of importance of the properties. Notice there are 3 properties and they are ordered according to their importance. These are the things which determine Alice's choice. And then there's a trigger. I'm going to consider the dynamics triggered by, in this case, triggered by some event. Alice wins a lottery. So Alice luckily wins a lottery prize of $10 million. This changed her situation dramatically. Now she considers the quality most important, then neighborhood, then the cost. She has enough money to buy a house. So those are the two examples I used for my dissertation, later on as one example for my research. And but the same similar ideas also investigating in other people's work. For instance, in economics, Digit and List in their paper 2013. The paper is called "Where Do Preference Come From?" They were also trying to study the reasons for preference. And this is their example. So an agent faces a choice between 4 different cakes. SH, S means sweet, H means healthy, a sweet and healthy cake. NS, non-sweet and healthy cake, a sweet and not unhealthy cake, finally a non-sweet and unhealthy cake. So these are the only possible possibilities if you have 2 properties. So then in their framework, they call these properties salient properties, and also argued these are the properties which really play a crucial role for the choice of the agent. In Jerome Lang and Van der Toren's work, so they also look at the dynamics of preference. The paper, if I remember, it's called From Belief Revision to Preference Change, something like that. So they have a few examples. This is one of them. Initially, I desired to eat sushi from this plate. Then I learned that this sushi has been made with old fish. Now I desire not to eat this sushi. So this is after I learned some new knowledge, I changed my preference. This is triggered by you learning something. And a different example also from their work is this one. It is a nice afternoon, and I would like to take a walk. Then it starts to rain. I do not want to have a walk anymore. So this change, in fact, is a physical one. It's a physical world change. It's not only mentally you learn something. So those can be also a trigger for preference change. Yeah, those are the examples for my research, for other people's research. And today I'm going to focus the following. So first I'll introduce a framework, reason-based preference. And then I'll introduce the situation where uncertainties occur, that we have to deal with beliefs. We have to introduce beliefs to account for the uncertainties. And then I'll generalize the framework into a structure model, 2-level models, and see how the 2-level model, 2 levels connected to each other in the study of preference. And then I'll end with some conclusion, the current developments. First, reason-based preference. So we just saw this example. Alice chose some house depending on these 3 considerations and the importance of their order. So this example put it slightly in a formal way. We call the considerations priorities, and then they form a priority sequence. In this case, we use a C as cost, denote cost, and Q is quality, and is neighborhood. So then I'll read this as CX is much more important than QX, much more important than NX. So this is much more important. So then let's assume Alice has the following information and consider regarding 2 alternatives, D1 and D2. For instance, she has D1, CD1, CD2, not QD1, not QD2, ND1, and not ND2. So given this information, we look at the priority sequence. We will say Alice prefer D1 over D2, and we will write pref D1, D2. So I hope this is intuitively plausible, reasonable to you, because D1, D2 has the property C, and D1, D2 does not have a property Q, and D1 has the property N, but D2 does not have the property N. So this will lead the final choice. D1 will be preferable than D2. So then in a formal language, a logic, we introduce a priority sequence as a finite order sequence of formulas, C1, C2 to Cn, and each Cm is a formula from the language. This language is a monadic first order language. So all these are predicates. You can think of they are properties concerning about objects. Objects has properties, and the properties are ordered in this way. There's exactly one free variable x common to each Cm. So among them, they share a common variable. So that earlier items here in the sequence count more heavily than later ones. So that's why I said C1 is much more important than C2. C2 is much more important than C3, and so forth. So then, given that priority sequence of length n, consider two objects x and y. We can define this binary relation pref xy as follows by induction. Overall, it's pref x over y is defined as pref n step or n stage x y. So for n, if we look at the first step, pref 1 x is xy, if and only if x satisfies the first property and y does not. So you look at the first property in the sequence from left to right. If you have x satisfies that property, y does not, then we get already the preference, clear preference. Then for k plus 1, the k plus 1 step x over y, there are two cases. Either at the case step, it's already clear, pref k x y. If that is not the case, we could get the final preference by looking at the k plus the first property. Here I introduce EQK xy as a auxiliary predicate. It means up to k, those properties cannot make a difference between x and y. We have to consider k plus first property. So this is the definition. Given a priority sequence, we can define in this way binary preference relation. So those are the basics about orders. I'm not going to go through strict linear order. If I call sequence, which means it's a linear order, because later I'll generalize the order into partial order. And then, yeah, those are the usual definitions for various orders. And then thinking of a logic system for this notion of preference. First, we have these properties. Actually, here, notice I used the underline pref, which is a non-strict version of preference. The definition I gave before, this is a strict version without underline. Now, this underline is a non-strict version of preference. So it's a quasi-linear order with the following properties. Those properties are also very intuitive. The first one is reflexive. The second one is totality. The third one is transitivity. So those are the three basic properties for the preference. And then we use P, this boldface P, to be the universal theory obtained from the above three axioms. And then for this system P, we can prove a few theorems. These are the two most important ones. The first one, of course, that's expected completeness theorem. We usually have to consider and prove. Phi is provable in this system P if and only if phi is valid in all quasi-linear order models. So this is completeness. Then more interestingly is the second theorem I call representation theorem. It says this: phi is provable in this system P if and only if phi is valid in all quasi-linear order models. These models can be obtained from priority sequences. So why it's representation? Because once we find the preference model, this model is obtained from priority sequences. So in terms of priority sequences, we get a preference here. So that's the representation theorem. I have a proof here, but I'm not going to introduce the proof. One thing I wanted to emphasize is, although there's a representation theorem here, but in fact, once you have a preference, the representation theorem gives you some reason, you can say, some reason. But it's not necessary, it's your true reason. That because this is extension, you can obtain from some priority sequences. It can be your true preference, a reason, two reasons, but it can also be just some reason which can interpret your preference. So that's the representation theorem. Let me go a little bit further to the dynamics in this setting. So remember this example: Alice wins a lottery. Then she no longer thinks cost is the most important. Now she considers the quality most important, then neighborhood, then the cost. So if you think of the priority sequence, this event, like winning a lottery prize, triggers a change in the priority sequence. So which means you have something which becomes most important. That's how the dynamics of preference studied here. So we are going to introduce 4 operations to account for possible dynamic change. I put it like those operators in brackets. Those are the dynamic operators. You can think of them like dynamic programs, dynamic logic. So plus A means we are going to add in A to the right side of the priority sequence. Right means the less important part. So the intuition for this operator is that some consideration become relevant. You sort of your preference, you sort of your priority sequence, but suddenly something become relevant. Okay, relevant is not that important, so you put it to the right. And A plus is you will put A to the left. To the left, that's the most important part. So this means something become most important. You didn't think of that, but now it become most important element you consider. So you put it on to the left. And then you could also drop the last element of a priority sequence. The last one no longer in your consideration, you drop it. And then another one is you switch the importance of the neighboring two elements. So that's this operator. So given any sequence, priority sequence, if we consider these 4 operators can be taken as basic ones to account for any possible dynamics. You can think of how this will be do the work. Because you always can switch, then you switch to the end, you drop something. So you switch something become most important. So those are the dynamic operators. And then this is a tradition of dynamic epistemic logic. If you have dynamic operators, you also want to have like a dynamic preference logic system. And you also want to prove the completeness of this logic and also think of other properties like expressiveness. And then what's useful is to get recursion theories, recursion axioms. The recursion axioms, sometimes it's also called reduction axiom. It reduces the dynamic formula to a static formula. If you look at these formulas, on the left side, it's all they all have the dynamic operators, and then on the right side, it's gradually get rid of the dynamic operator. Dynamic operator become the static logic language. So then the completeness proof can be reduced to the dynamic completeness result. So I'm not going to say more about this. This is I just want to say we can have this set of recursion axioms for these 4 basic dynamic operators. Yeah, that's end my first part. I hope by now you get some idea how we account for the reasons for preference, or in Van Richter term, extrinsic preference is now represented this way by a priority sequence. So the priority sequence intuitively are considerations an agent would have when the agent form her preference. So next is a model for preferences and beliefs. Beliefs are a notion that deal with uncertainties. If we have complete information, we don't need to have belief. Only when we are uncertain, we rely on our beliefs. So this is a variation of the previous example. Alice is going to buy a house. The first part is similar. Consider 2 houses, D1, D2, that Alice hopes to choose from. Alice only has partial information. So it's no longer the complete information that we assumed in our previous example. So now she only has partial information. Let us assume that she believes that D1, D2 have the following properties. Remember in the previous discussion, we say Alice has those information for sure, but now she only has partial information, but she believes, according to her available information, she believes the following. So which means we are going to put B in front of those formulas, somehow put it in front. We need to think of how to put it in front. Where should we put? So she has this information. She believes those properties. Now, as I said, the question is how to put B in front of those formulas, and how do we define a preference under uncertainties. So one proposal is I call definition 1. Given a priority sequence of length n, this is similar as before. So we don't have a we don't have a belief on the priority sequence. This is clear. The uncertainty is about the information object has a property or not, but it's not an uncertainty that the agent has for the given priority sequence. So pref x y is defined as follows. Notice the only difference is b. So now we have a b c1x. So at the first stage, x is preferable over y if and only if the agent believes x has the property c1 and y she does not believe. It's not believe. She does not believe y has the property c1. So this is the crucial. If you see the first stage, then the rest is trivial. So this is the definition, one possible definition. Now we can define the new preference according to a given priority sequence and the agent belief. The agent belief is used this way. Of course, for EQ, we still need to add B. So those are the usual things. The rest is similar. Then I'm using several agents to consider, to compare different definitions. I'm going to give three definitions, three possible procedures. This is the first one. We think of Alice. Alice favors the definition 1. She look at what information she can get. She read that D1 has a low cost. About D2, there's no information. So this is a situation. D1, she has information. D1 has low cost. About D2, there's no information. And this immediately makes her decide for D1. According to this definition, she will stick with this decision no matter what she may hear about quality or neighborhood. Put it in formula, we can represent Alice's belief as follows. Alice believes D1 has a property C, and Alice does not believe D2 has the property C. So this is it's not the case. She believes D2 has the property C. So then this definition 1 gives us a priority, the preference. Alice preference D1 is preferable over D2. So this is the first definition. Let's see the second option. So notice the second option, actually, we are still using B, because this is the same uncertainty, but now the negation has a different position. We put negation in front of a C1Y. Previously, we put negation before B. Now we put negation before C1Y. So this means at the first stage, for instance, X is preferable over Y if and only if the agent believes X has the property C1 and the agent believes Y does not have that property. So this is very different, right? This is much stronger than the previous version. You have to believe something, not the case. It's not the case you believe something. So similarly, we consider Bob for the second definition. He gets the same information as Alice, but he has no preference and will remain so as long as he hears nothing about the cost of D2, no matter what he hears about quality or neighborhood. So on the other hand, now we, as before, Bob also has a similar information as Alice, BCD1, not BCD2. That's why Alice, according to this information, Alice can make her decision already, but not for Bob, because Bob requires something stronger. Bob has to get B not CD2. So that's why, but we don't have this information. That's why Bob cannot make his decision. And the third option still is also interesting from a slightly different intuition. So here we introduce a superior x is superior to y, means objectively x is better than y. So that's a superior means. So all up to n, we are using this superior instead of preference. But the preference eventually is defined as a belief of superior. So pref xy is defined as belief x is superior to y. So then this is a before that, superior are all objective information. We don't involve any belief from a superior one to a superior n. And this is interesting. Let's look at the third agent, Carol. So she also has the same information as Alice. On that basis, Carol cannot decide. But some additional information about quality and neighborhood helps her. Remember, Alice, whatever the additional information, she already decided. But now the Carol cannot decide, but some extra information can help her decide. For instance, when she hears that D1 is of good quality or is in a good neighborhood, that's for D1, it's or. And D2 is not of good quality and not in a good neighborhood, that's for D2. So then Carol believes that no matter that D1 is superior. Those are the objective information Carol gets. So D1 is her preference. Maybe formula will be much clearer. So we have CD1. This is CD1 is her information, and similar to Alice. This is all three agents have all the same information, CD1. And then she also has QD1 or ND1. D1 has either of this quality, this property. And for D2, D2 does not have Q, does not have N neither. So these are all her information. But then according to our definition, actually, objectively speaking, D1 is superior to D2. Then we can say, okay, this is her belief. She is still uncertain, but according to her available information, she has some judgment about superior D1 is superior than D2. Then she can say she prefers D1 over D2. So I give these three definitions. They are interestingly different because we put B, the operator belief, in different places in the definition of preference. And then also this leads to interesting properties they have. So first, of course, I emphasize these three definitions can be seen as three different procedures to obtain preference. And we can also see already by the example, totality holds for the first definition, but not for the second and third. And then among them, the three definitions, the second one implies the first one, the second one also implies the third one. But the first one and third one are incomparable, especially the third one. It's a different intuition. And then in terms of the logic, interesting theorems are the following. Considering non-strict version of preference, we have a pref x, y. If and only if B, we can add B, pref x, y. And the negation also holds, not pref x, y is equivalent to B, not pref x, y. So this is for the first definition. Okay, so this is for the first definition. then for the system, logic system, we call BPref. BP system consists of the following validities and also the usual NP rule and generalization for B. So the first three we have seen already. They are those three basic properties for preference. And the four is the one we just saw. And actually the four is very interesting because it's about a connection between belief and preference. And then from 5 to 8, those are the usual KD45 axioms for belief. And the model is formally defined as KD45P models. It consists of those elements. W is a set of possible words, like a Kripke model. And D is a set of constants. R is a relation, which is a belief revision, Euclidean and serial accessible relation. And then this is the relation, preference relation at possible word W. So basically, the model is the if you talk about if you talk about beliefs, it's a possible word. From one possible word to another, you have belief doxastic relations, and at each word, you have objects, and the objects have preference relations. That's basically the model. And then similarly, we have completeness theorem for BP system, and also a representation theorem. So the representation theorem, similarly as the one before, it says that phi is provable in the system BP if and only if phi is valid in all KD45P models, where in each possible word, all the constants are quasi-linear ordered. Those are the completeness part. And then this order on the base of a priority sequence. So this sequence, again, can be served as a reason which by which we induce the preference ordering about objects. That's the representation theorem. Of course, also I extended this setup to multi-agent system. So we can also define for each agent, there is a priority sequence for that agent. If you have many agents have different priority sequences. So then if you are thinking of a multi-agent, then the agent can be cooperative, they can be competitive. If they are cooperative, you can understand that they share the same priority sequence. If it's a competitive agent, they may have the opposite priority sequence. So this I'm not going to say more, but those are the interesting issues if you extend the single agent case to the multi-agent case. And then in this setup, on belief and preference setting, it's also possible to consider dynamics. And here I just give one example for belief. Of course, the dynamics of the
Is this me or is it the speaker?
Mine is frozen.
But you're not. Okay, here we go. No. Oh, we lost you there for a minute.
Okay, so this is a dynamics that happens to the belief part. again, this operator is a dynamic operator. You can read it as learning A, or A is announced. So something A is learned, then X is preferable over Y based on the sequence C. So this would be like a recursion axiom, would be equivalent to A implies this part. A implies this part. Notice the sequence has been changed into A implies C. A implies C means in the sequence, we will replace each item by A implies that item. So this is the dynamics of belief change that lead to preference change. Yeah, this is the second part. I introduced uncertainty, and then in logic we used language belief to describe the uncertainty. And then in this system, we can also, interestingly, we can have several definitions to define preference. And now we can also consider the dynamics of preference. And now let me go a little bit general. So far, what we have seen is a linear ordered priority sequence. And in the following, I'm going to extend that to priority graphs. Graphs means you allow two nodes incomparable, which is partial order. So I'm going to call it priority graphs. And then the second, now, so far I have introduced those dynamic operators as individual operators. I have not really combined them in any possible way. So I'm going to introduce the dynamic operators in a PDL program format. So then you allow sequential choice or other possible dynamic operators. And then most importantly, actually, I want to show is the final part. So far, we have one level priority sequence, another level preference, derived preference. But this two-level perspective, I'll introduce it in a priority graph. And I also introduce their dynamics. In each level, they have a certain relations. That's an interesting way to look at preference and priorities. So priority graph. So the graph is this. In general, you have order, then you have these propositions. You can think of propositions as in a graph nodes, and the nodes is a property. You can think of this very intuitively, and they are ordered, partially ordered. And then once you have a priority graph, similarly, we can derive or induce a priority, a preference based on this priority graph G. So for instance, X, Y, X is better than Y, or X is preferable over Y. And we consider this is only one possibility. So for all P's in this old phase P, for all properties, if Y has the property, then X has property. Then we say X is better than Y or preferable than Y. So this is only one possible way of inducing preference. Actually, in the literature or AI, people also discuss like a goal-based preference. Technically, it's very similar. If you have several goals, if the goals are ordered, and then you can derive your preference over actions. So then you can have various possible ways of defining the preference. So I'll take this only as example, running example or running definition for my remaining discussion. So this is one level. We have priorities. They are intuitively they are considerations of an agent and the order of importance. And then on the other level, now I'm going to abstract object into a Kripke model, which is a basic preference model. We have W. So W now has possible word, but to connect with the previous discussion, I was talking about objects. You can also think of possible word as objects. All objects as possible words. They abstractly they are the same thing to me. So W is a set of possible words. This relation is a reflexive and transitive relation, and I'll call it Betterness preorder. And V is a valuation for proposition letters. So this is the usual modal logic model we are familiar with. Then the language also is a modal language, consists of this, and then this bracket, diamond. This is a non-strict version of preference, and this is a strict version modality for preference. And then we have E is the extensional universal modality, E phi, exist phi. So in this language will be used to discuss this model. And then the two levels eventually come into together by this theorem. This is we have this model, the modal models W relation and V, be any modal model whose relation is a preorder. Preorder just like defined previously, preference order. The following two statements are equivalent. First, the relation is a reflexive transitive order. This is the property of a preorder. And second, there's a priority graph. There is a priority graph such that for all words x, y, x has a relation, this preference relation in this model, if and only if this relation is based on the priority graph. I think by now you will recognize this is kind of representation theorem. You have x is better than y or preferable over y, but if and only if that relation is based on priority graph. So then this actually connects the two levels together. And the PDL program view, okay, I have only 5 minutes left. I want to stop. So PDL, I'll quickly say this. So we are going to define the dynamics in terms of those dynamic programs. Start with test, then you have R relation, the preference relation. You also have the strict relation. Then you have the universal relation, consequential relation, consequential operator, and the choice. So those are the usual PDL program operators. Then given any dynamics, possibly to change the preference, we can use these terms to express. And this is a result we proved. Pi is a preference change program as defined above. There's a complete dynamic preference logic for pi, and its recursion laws can be computed automatically for both the weak and strict Betterness modalities. Basically, there's an interesting automatic computation you can do to get a reduction axiom. Again, if you get a reduction axiom, that's helpful to think of completeness proof. And then the dynamics, that's the dynamics on the preference relation. We have our strict version. Now at the priority graph, we can also think of dynamics. For instance, here, I'm going to introduce only those. You can have a new property suddenly add to the graph. You can put two graphs sequentially, one on top of the other, or you can put them in parallel. Those are the possible graph changes you can think of. Of course, those are studied by other people, Andreka and Gerard. So I'm not going to say more. But this, I'll skip the definition, but I'll show you two diagrams. So basically, if you look at the upper level, you have a graph, you have a order. Then you add some new consideration, put it in parallel with the graph, you get a new graph, and then also relation. So this is the dynamics that happens at the level of a graph. And then from the top to down, lower level, this arrow means according to some definition. For instance, I show one definition, right? For all P in both P, if Y has the property, then X has the property. Keep that in mind. That's the definition we get preference relation from a graph. So then we get a relation over possible world. So then at a possible world, actually, you can also think of other operators. Those operators has been studied. And this operator, usually I call it a suggestion. A is a suggested, means in the new model, not A will never be preferable over A. After suggestion of A, not A word will not be preferable than A word. That's what suggested A means. So then it's interesting result. If you look at this, if you go from the upper level, you get this. Then if you following the definition, deriving a preference from a graph, you get this exactly same preference relation. So you go this way, or you go the upper than down, you get the same preference. This holds for suggestion. This and another example. This is also you put A on top of the graph, and here you have another operator. This is called radical upgrade. So this is put all A's on top. So I'm not going to say more. If you have questions, I can explain more. But the good result does not hold everywhere. We also have result like negative. The deletion operator is not BDL definable. Those are related to the definition of definable. I'll skip it. Okay, let me conclude. So today I basically what I did is to illustrate reasons for preference and preference change in natural concrete scenarios. Then I presented a logic model that can deal with reason-based preference and with complete and incomplete information and also acts of preference change. And finally, I quickly extended this work to a more general setting so that we can relate two levels of preference, static and also dynamic. After this work, actually, there are further developments. For instance, in rational choice theory, I already mentioned Dietrich and List work, and Osherson and Weinstein also has some work. And I working with my student also using more probability and utility functions to study preference. And in deontic situation, I had collaboration with Benta-Grossi to introduce priorities into the deontic semantics to provide reasons for ideal reality relation model that the deontic logicians usually use. And I'll skip the game theory. Finally, in recent years, I have been working with maybe you know Patrick Gerard and Jeremy Seligman from Auckland University, I'm working with them in social network logic. There we consider social influence. Say if I have a certain preference, how my preference would change given my neighbors or my friends' preference. And then some further issues that have not been studied, I want to also mention. First, preference change over time. So far, I haven't seen much about logical work and temporal logic combined with preference, because there are interesting issues there. For instance, you want to track the consistency of preference over time, how to do that. And the second is a different intuition. Now we are talking about preference. Actually, there are also discussions in the literature about good enough, satisfaction. Those are the interesting notions to discuss when you compare things. If we take this notion, what will be the logic? And then interface preference logic with AI. These are the ongoing project I'm doing with my students and colleagues. One is to connect preference logic, this reason-based preference model, to question of why. You can see from Fenrong's quote, if someone asks you why you like this wine over the other one, okay, you can say, okay, because that's my doctor told me, or it is good for my health or stomach. So you give an explanation, or you give a reason to answer a why question. So we are looking at this. And preference and the recommendation system. This is also working with AI people. Recommendation system basically about recommend your possibly preferred objects. But the current framework they are adopting, or algorithm they are adopting, has not considered reasons for preference yet. So that's the direction I am working on. So I think you can see these are really the possible topics for collaboration between philosophy, cognitive science, computer science, and AI. I hope you guys will be also interested in looking at some of those. Thank you so much.